把它放在中间会小。中间这有都上。要不用收纸啊。都上过。够啊，因为这样够先放，好不好？耶！我手上还有2只已经抱出来了。
没有一人一只。
对啊，我已经在发我的
学生就摆
他们如果用习惯的话，
好，那我这2只都摆在这里，好不好？没关系，先这样。再过一层。你有什么问题哈？你就查后面的公主他就过来问。现在没问题。对，先开机线。好。要有声音，看声音大小，我觉得好大声，太大声我们
喂，太大声。喂，测试。麦克风声音1、2、3、1、2、3。
喂，1、2、3。
麦克风声音1、2、3、1、2、3。
学生给他听这个话。
麦克风声音1、2、3、1、2、3。
喂，1、2、3。
麦克风声音1、2、3、1、2、3。麦克风声音1、2、3、1、2、3。麦克风声音1、2、3、1、2、3。麦克风声音。
喂。
麦克风。喂，麦克风声音。麦克风声音。
喂。
麦克风声音。
这样，喂，这样就会到，很好讲话，手会低头大脚都没问题。
我买了，还有多一次的。
连都有。
不够4只，可能就不备了。原本是备2只的。就这只不能用。
上也不用讲，不然。
喂，1、2、3，1、2、3。
台湾11、1、2、3。
拿给我看一下，在你的投影上面。这个样子。
高规格，高规格的只是我们那没办法，那边老师都可以。最好的办法就是。 对，大部分会在家里之外。对。
不好意思，那个先设计一下，先装。
这一个，那个。
今天比赛的3个先那个装一下那个检测一下那个投影。
今天早上我就哎呀，你讲的话，你带着每个学生，他都没有影响的。
说那边的，会议。
靠这这样。OK 啊。
谢。
就分出来，1、2、3、1、2、3，按这调整它那个气体，就收音的那个档，好吧？1、2、3，1、2、3，就是这样子。OK， 太小的就拉过来一点，太紧的话它会引爆成大，出来一点这样，好不好 ？OK。
All right.
最近封起来，我觉得手还蛮危险的。说应该是最近发生的。
Good morning, ladies and gentlemen. Today is the final physics flight of 15th PYPT. So I would like to start the final flight section now, and starting from introducing all the members on the stage. And then today we will, our schedule is a little bit different from the regular physics flight. Usually, opponent will challenge the reporter for problem, but today, reporter already choose their problems, so we will start our schedule from preparation phase. Okay, so I would like to start from introducing the jurors, and then all three teams on the stage. So, how about Professor Jia?
Hi, good morning. Hi, good morning, everyone. I'm Professor Jia, a physics professor of Department of Physics, National Taiwan Normal University. And I hope this fight I can learn more. Thank you very much. Thank you. Hi, I'm Chen Zhonggao from National Taiwan Normal University. This is the first time that I attend this final fight. I'm glad to be here. Okay, good morning, everyone. My name is Wen Qinlin from National Taiwan Normal University, and I hope everyone enjoyed this morning.
Hello, I'm Ho Min Guang from the National Taiwan Normal University. Retired. I hope everyone has a good day today.
Good morning, everyone, including those sitting there. I'm Xiang Han Cai from Physics Department, National Taiwan University. I hope everybody has a good time today. Thank you. Good morning, everyone. I'm徐有庠from Physics Department of Physics in Taiwan University.
Good morning, everyone. I'm Mohan Lee from Singapore. Hope everyone enjoys the moment. Okay.
Good morning, everyone. My name is Dr. Xie. I'm from Economics Institute of Economic and Political Science. Thank you. Good morning, everyone. I'm Chu Fu from National Taiwan University. You have a good time.
Good morning, everyone. I'm Coming from National University. Thank you.
Good morning, everyone. My name is Fang Yulo from National Taiwan University. I wish everybody have a good enjoy the morning. Thank you.
I'm Dongyan Xu. I will be the chairman of this morning section. I'm from Taiwan Normal University. So then I would like the reporter, captain, to introduce your team members.
Good afternoon. I'm the captain, Terry from Cleveland Southfield. These are my teammates, Zhang Yufei, Li Guanxian, Chen Yingtai, and Lan Shaochen. Thank you.
And opponent team, please.
Honorable jury and fellow competitors, I'm the team leader from Team Galileo, and my name is Hong Bingwei, Zhang Weixin, Cai Renfang, Lin Shiyao, and Bo Yuan.
And last one, the reviewer team.
Okay, hello everyone. I'm the leader from Team Epsilon from Foshan Senior High School, and my name is Xu Yizhen, Xie Haorun, Chou Yuzhe, Wang Lingsheng, and Li Haozhe for my members.
Okay, thank you. Okay, just as I already mentioned, the problem already been chosen. So this morning, the first section, the problem to be used would be number 2, oscillating sphere, presented by L. Fire. So now I would like the clerk to start. We will start from the preparation of the reporter for 5 minutes. During the preparation phase, reporter please write down the presenter's name on the paper. the preparation time is almost up. So, reporter, please start your presentation for 12 minutes, please.
Honorable juries, fellow competitors, this is a report from human sphere. Reporting problem number 2, oscillating sphere. Problem statement. The light sphere with the conducting surface is suspended from the thin wire. When the sphere is rotated about its vertical axis, hereby twisting the wire and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. Due to the problem statement, I believe that we should focus on the investigation, how damping effect acts on the light sphere, and how do different parameters, for example, the size of the sphere, magnitude of magnetic field, etc., affect the motion of the sphere. This is the outline of our presentation. First, for my preliminary experiment part, I'll use my observation video to demonstrate the phenomenon. In this part, I'll focus on the qualitative explanation about how this phenomenon is caused. And next, I'll introduce my theoretical model regarding the Ohm's law, Gauss's law, Poisson's equation, and moment of inertia. Next, my experiment parameters include the magnetic field, induced angle, and conductivity of the sphere. Last, I'll talk about my conclusion. Preliminary experiment. This is our experimental setup. First, we use a thin wire for about 50 centimeters to suspend this conductive sphere. Next, we use the Helmholtz coil with 130 rounds to provide a uniform magnetic field inside the system. And this is how we measure the conductivity of the sphere. Through this formula, we are able to know that this is a cross-sectional area of the conductive sphere, and also this is the electric current of the sphere. And these are general formulas for the potential difference in the electric resistance of the sphere. And through having two electrodes to test the electric resistance of these two parts, we can then get the R inside here. And then we can know the sigma, which is the conductivity of the sphere. Next, in order to verify that we are able to use this formula inside our experiment, we actually tested 100 data points for the surface between the coils to measure that the magnetic field inside this part can be, the amperes that we are giving to the Helmholtz coil can transform into the magnetic field can be assumed as this. And after verifying, we found out that by giving the Helmholtz coil a 2 amperes of electricity, we can get that it's about 1.55 millitesla. Through the observation video, you can see that from the left-hand sided one is the one simply rotating, while the right-hand sided one is the one rotating with the Helmholtz coil. From this chart, you can see that it causes a significant damping effect when a uniform magnetic field is added inside the system, and this is the damping effect. Next, I'll first explain about the torsion tensor. We're giving an angular displacement for this conductive sphere. It causes a restoring torque to try to make it restore back to the equilibrium position. However, it does not stop in the equilibrium position. It actually rotates to the other side and keeps repeating this motion until it stops. And the reason that causes its damping in this condition includes the air resistance and reflection at ECU suspension. In a normal situation, when you're using a conductive outer shell, the sphere rotates about its vertical axis, while these conductive particles make circular motion, which causes a really thin electric current in this part. However, in our experiment, since we know that the charge distribution is restricted between the T, which is the shell of the conductive surface, and when the thickness of the conducting surface T is way much smaller than the radius, then we can know that the radius component here can be ignored. Next, I'll explain about how eddy current is formed inside this system. So today, when a Helmholtz coil is giving a uniform magnetic field from the left-hand side to the right-hand side, and since we know that the metal flow is basically an integration of infinite 2D coils, so in this part, I'll explain the metasphere by using this 2D coil. So when this 2D coil is rotating about its counterclockwise direction, then it causes from one side we can know that it causes the contact area for the magnetic field to increase, and then causes the eddy current to rotate in this direction. And this is how eddy current is formed inside the system. And through the eddy current, we know that the I inside the Lorentz right-hand law, and also we know that the magnetic field inside the Lorentz law given by the uniform magnetic field. So through Lorentz right-hand law, we can know that there's always a Lorentz force going in the opposite direction where the magnetosphere is trying to rotate. And this is why it causes a significant damping effect when the system is rotating with a harmless coil or a uniform magnetic field. Next, I'll introduce my theoretical model. So this is the general formula of Ohm's law. And so what we want is a current density J. So since we already measured the conductivity, which is a sigma here, first we want to know about the magnitude of V cross V. And after derivation, we know that V cross V equals to this part. And in our theoretical model, we're using the coordinate system. So these are the coordinates. Next, since we already know V cross V, from Gauss's law, we are able to know the rho T, which is the charge density. And after inputting back into this formula, and through Poisson's equation, we can then get the phi T, which is the electric potential here. And after inputting back the phi T into this formula, we can get the electric field and back into this part. So since we already know the F, which is the Lorentz force here, we can then get the torque inside the system. And after derivation, we can know the angular acceleration and also the decay time, which we set as delta equals to 4 rho F divided by sigma and V squared. And the oscillating spirit declares exponentially, which the angular inside our theoretical model, we set the omega as the oscillation frequency. So it is proportional to E but powered by negative T divided by decay time. Next, experiment. So after comparing our theory line with our experiment data, we found out that our data actually decays faster than the theory predicts. It is because the original theory is only considering the damping caused by magnetic field, but it ignores some of the parts, for example, the damping caused by friction and air resistance. So in order to make corrections or modifications for a theory, we actually need to conduct an experiment without the magnetic field. And then by fitting, we can know that there's a damping coefficient without the magnetic field. So the damping coefficient is gamma inside this. So after combining damping coefficient with the original magnetic field damping coefficient, we can then get the correct theory. So after modification, we can know that this is a theory line with the frictional force added. First experiment that we conducted is by changing the magnetic field. We changed the magnetic field by giving different amperes for the compound spool. And through this formula that we proved we can use, we actually, by increasing the amperes given for the compound spool, we increased the magnetic field from 0 millitesla to 1.6 millitesla. And we found out that when the magnitude increases, the decay time of the angle decreases, and the rotational frequency will be constant. So after comparison with after turning all these maximum angular into absolute value, we can compare it with our theory line. So we can find out that there's actually much deviations when it's only 0 millitesla given from the whole spool. It's because that most of the damping inside this line is caused by air resistance and also friction and suspension, which means that it is more related to the initial condition of the releasing, which causes the bigger deviation, since most of the damping are not caused by the magnetic field. And from this formula, we can know that when changing the V here, it causes the decay time to decrease, which causes when the decay time decreases, it causes the system to have a more significant damping effect. The next experiment that we conducted is by changing the induced angle. And this is the oscillating axis toward the wire. And so we want to know the horizontal component of the magnetic field. So when it's perpendicular to this axis, it actually has the biggest, when it's 90 degrees, it actually has the biggest this part, and causes the decay time to be smaller. And from this, we can know that when induced angle increases, the decay time of the angle decreases, and the rotational frequency also is the same. And that is because we make the decay time in this part to decrease. The last experiment that I conducted is by changing the conductivity of the sphere. I changed the material for the conductivity and put the conductivity sigma into this part. And so when the sigma is greater, it causes the decay time to decrease. And due to the low conductivity of the phenomenon, so the bronze, we actually changed two different materials, which are iron and bronze. And because the bronze is having a low conductivity, therefore the phenomenon is actually not apparent. In conclusion, by modifying the theory, which adding a magnetic, this is the original theory, it only has a magnetic force damping coefficient. By modifying the theory with new damping coefficient for friction, we can make the theory line to fit with our data as well, because we modified it. And for the first experiment that we conducted, we increased the beta, we increased the B, which is the magnetic field here. And it causes the decay time to decrease, which causes a more significant damping effect. And for the second experiment that we conducted, which also found out that the decay time of the same angle increases and the rotational frequency will be constant. And it is because that we make the decay time period smaller, which causes a more significant damping effect. And for the last experiment, we changed the conductivity, and because the bronze conductivity is really low, so the phenomenon is actually not apparent. And this is my conclusion.
Sorry, time to stop.
Thank you.
Now, opponent, please ask a question to the reporter.
Okay, thank you for your presentation, and I have a few questions about your reports. First, please turn to page 5. The one that shows the preliminary experimental setup with a coil and a sphere. Okay, so is the coil you use here a hand-pulled coil?
What can you rephrase?
Is it a hand-pulled coil that you use in your experiment?
Yes, I'm using a hand-pulled coil.
Okay, so what is the relative size of your sphere and the coil? Your relative size of the radius of the sphere and the radius of the coil.
I didn't measure the radius of the hand-pulled coil.
Okay, thank you. You've answered the question.
But the radius of the manosphere is 10. The diameter is 10.
Okay, thank you. Now please turn to page 24. Okay, so here you mentioned the difference notation of gamma and delta, and can you briefly explain what the two notations stand for?
Which part?
Yes, in your equation, you have the notation gamma and delta, and can you briefly explain what the two parameters mean?
The delta is the decay time, which means that the decay time is a definition when, for example, this is 100%, and decay time is when it reaches to 37% of the original amplitude.
Okay, thank you. So what is the notation of gamma?
What is the rotation?
What is the notation of gamma? What does that mean?
Rotation of alpha.
Notation of gamma. What does that mean?
Notation of. Sorry, can you?
You have theta naught E minus gamma T minus T over
gamma. Sorry, gamma.
Yes.
So gamma is the friction coefficient, damping coefficient. Friction damping coefficient.
Okay, thank you. In your theory, did you write down an equation of motion you predict in your theoretical model?
Please turn to Ohm's law.
Okay, thank you.
Okay, time is up. Now is the preparation time of the opponent. Time is up, so opponent please take the stage for up to 4 minutes. The remaining time will be added to the discussion, so please start.
Honorable jury and fellow competitors, I'm the opponent from Team Galileo, and today I will be opposing question number 2, oscillating sphere. And this is the problem statement. And we believe the main purpose of this investigation is how the magnetic field can affect the damping effect and affects the motion. And the main focus of the reporter's report is the damping effects on the sphere and the different parameters affect the motion of the sphere. Okay. And for the theory part, the reporter used multiple rules in electromagnetics, such as Ohm's law and as we demonstrate in our presentation, and eddy currents and Lorentz force. And for the experiment parts, the tools they use a hand-closed coil to create a relatively stable magnetic field, and they use a wire and a sphere to create the situation provided in the phenomenon. And for the parameter, they changed the magnetic field, and they also changed the induced angle, and they also mentioned the effects caused by the conductivity of the metal. And for the analysis, they used a checker for oscillation and rotational analysis, and they also mentioned the conception of the energy decay, and they introduced relative parameters like gamma and delta, and they used the exponential function to describe this phenomenon. And for the conclusion they reached, the first one is when the magnetic field increases in the k time, whereas it decreases. And the second one is when they change the induced angle, the rotating frequency is constant. So here are some sentences and suggestions for the reporter. For the pros, first of all, is to measure the magnetic field by using the formula in the model of the hand-closed coil. And the second one is the detailed experiments which demonstrated in their videos. And the third one is they can explain when does the damping come from, which is explained in their theoretical model. And the fourth one is they consider the air resistance by combining vector gamma into the resistance constants. And for the suggestions, first of all, we believe that in the presentation we did not see a theoretical equation of motion derived from the theoretical. The second one is there was a quantitative comparison between the theory and the experiment. And the third one is like parameters, like changing the direction of the eddy currents, which we believe that the reporter did not mention in his presentation. And also in the presentation, the reporter mentions that the model of the sphere can be viewed as a permutation of the coils being put together, and this one will be in our later discussion. So these will basically be the outline of our later discussion. For the first phenomenon, we will discuss the damping effect, and we'll discuss where the damping effect comes from, and why can a magnetic field exert such effect on the sphere. And for the theory parts, basically these will be the points of discussion, and also we'd like to derive the equation of motion from the expression of the magnetic torque provided in the reporter's presentation. And that's the end of my presentation. I'd like to start my discussion with the reporter now.
Reporter, please get down to the stage, and we start the discussion now.
Okay. Now please turn to page 7. Okay. So here, can you briefly explain what this graph stands for?
What this graph stands for?
Yes.
Also, we measure 100 data points from Gauss's meter. So in order to prove that,
Can you say? Can you speak slower, please?
Oh, we measure 100 data points between the surface for the surface between the coils, and we use Gauss meter for the measuring of the magnetic field between the surface to prove that we can use this formula. For example, by getting a 2 amperes of the electric current here.
Yes, and this formula is based on the assumption that you use a hand-closed coil. Yes.
Yes.
Okay, thank you. And now please turn to page 10. Page 10. Okay, so here you have a conductive outer shell, and can you tell me what the material is?
Well, we're using iron and also we're using iron and bronze for the material.
And what is this conductivity? As mentioned in the presentation, that the conductivity can affect the motion.
One of the conductivity for a smaller one is 37.08 times 10 powers of 6, while the other is 63.01 times 10 power of 6 Siemens per meter.
Okay, thank you. So here you have the outer conductive outer shell, and I want to ask what is your inner parts of the shell?
What can you rephrase the last one?
Okay, so let me rephrase the question. For your sphere, only the outer parts is conductive.
Yes.
And what is the material of the inner parts?
It's the same, like it's the same material, but it's hollow sphere.
Okay, thank you. And okay, so now please turn to page 12. Okay, so here is your explanation that you think that we use the board. That a conducting sphere can be viewed as a permutation of many rings, like this. Is that your point?
It's actually like 2D coils like rotate and wind like in the same axis, so it can be integration of 2D coils.
Okay, so here you introduce the conception of a coil. So now can you tell me what is the direction of the eddy currents in your theoretical model?
So as I explained, so for example, today this conductive sphere, metal sphere, is rotating about its counterclockwise direction, so it rotates in this direction. So we can assume that it is a 2D coil rotating in the counterclockwise direction. And because that the area that contacts with the magnetic field here is increasing, and through Lentz's law, we can know that when increasing, it also
based on Faraday's law.
Yes.
What? Based on Faraday's law. That's how you determine the direction of eddy current.
Oh yes. So when it's counterclockwise, the eddy current looks like it's in this direction, as I mentioned.
Okay, thank you. So now you turn to the page that shows your theoretical derivation. Okay, so in this that's why we'll just leave it here. And so in this example, which situation are you considering? Do you consider a uniform magnetic field which is perpendicular to the rotational axis?
Oh yes, it's perpendicular with the rotating axis, and we're only considering a hollow sphere with uniform magnetic field given by compass.
Okay, thank you. So now can you please turn back, and I'll tell you when to stop. Just turn back. Yes, go on. Next. Okay, thank you. So yes, the last page. Here you say the oscillating sphere accelerates exponentially with omega is proportional to an exponential function. Is that correct?
Yes.
Okay. So, however, now please turn to the pages that show your experiments. Okay. So here you have the relation of the oscillating angle and time, and obviously in this example, excuse me. The direction of the omega as mentioned.
Oh, the omega inside is actually the rotational frequency.
Yes. But the omega, since the rotation, it may turn in the other points, which means that under some occasion, it can go down where the omega is smaller than 0. However, in your theoretical derivation, which omega is proportional to an exponential function, which is always bigger than 0. So how can you explain this?
It is rotational frequency, so the frequency will not be negative.
Okay, so can we define rotational frequency?
Of this rotation.
So can we define this frequency?
How can I define this frequency?
Yes.
Like it's divided with like e powered by negative t divided by the k time.
Okay, so now okay, so.
And where's the negative part that you're seeking?
Yes, because in my opinion, the omega here is not rotational frequency, it's the angular velocity.
No, but I mentioned we identified that as the oscillation or rotational frequency.
Okay, so now you give a definition of rotational frequency.
Also, rotational frequency is like when it oscillates back to equilibrium position.
That is a period.
Yes, like the frequency of the this.
Okay, so in your definition, when it comes back, like here, okay, so here is your theta and t graph. So this is a period. Yes. So your definition of frequency, is it like this? Because I haven't heard what is your qualitative. Yes, so that is your experience. Now please turn back to the page of the theory. The last page. Yes, so here you have the notation partial omega, partial t. But as you just agreed, that your definition of the angular frequency is 1 over t. But t in your graph are these values. So which means that it may not be a continuous function. However, you differentiate it with respect to time. And here you have tau equals I delta, which I believe you should write tau equals I alpha, which means is a rotational form of Newton's second law. So this partial omega partial t should be the angular acceleration. So if this formula is correct,
yes, I agree. Like this part is angular acceleration.
Okay, so here the omega has to be angular speed. If
no,
omega
is like the oscillation frequency, but
if it is an oscillation frequency, you differentiate it with respect to time, but it is not the angular acceleration.
And this part, I mean, it's potentially related to this part. It's because I'm talking about the damping. It's under damping. It's the under damping situation that has the exponential.
Okay, thank you. I think we have to move on to the next part. Now, can you? So now you have the relation between the tau equals to this term, and where we can see that from here that the torque is proportional to omega. Is that correct? Yes. Since all the rest is a constant, so I'd like to ask that how can you derive your equation of motion from this expression?
You want to discuss the mathematical parts inside this?
Yes, I will discuss the mathematical parts of your presentation.
So I would like to suggest discussing about my current data and also not.
So you don't want to discuss the mathematical parts of your presentation?
Yes.
Okay, so let's move on to your experimental results, please. So now I'd like to ask another question about your experiments. Can you mention again what is the relative size of the radius of the sphere and the radius of the Helmholtz coil?
The radius of the sphere is 10. The diameter of the sphere is 10 centimeters. Well, I don't have to remember the radius of the. Oh, you mean the radius?
Yes.
Actually, oh yeah, I didn't remember the radius, but we calculated that. But
okay, so please turn back to page 5. The one that shows a preliminary, yes, this one. So from this observation here, we can see that the size of your sphere.
This is like demonstration. It's a model.
Okay, so do you have a real picture for that?
That's my picture.
Do you have a real picture of this?
Video. Sorry. Observation video part.
Okay, so here this is the size of your coil and this is the size of your sphere, right?
Yes.
Okay. So here, I think that since your size of the sphere is not relatively really small, and I think that maybe you have to make sure that it stays in the center, because even if it's Helmholtz coil, the magnetic field is not always uniform.
Make sure that it's in the center.
Sorry, that is okay. So, opponent, please summarize the discussion for 1 minute.
From a previous discussion, basically we had a discussion over the theoretical parts of the theoretical model. And in the experiments, the opponent believes that the reporter did not understand the notation of the experiment, since he mentions that the omega is the angular frequency. However, he differentiated with respect to time to show that the value of the angular acceleration. So the opponent believes that the reporter should understand the theoretical model of in his presentation work. And as for the experiment parts, we believe that the Helmholtz coil size is not relatively big to the sphere, which means that under some notation, the magnetic field, which has a flux over the sphere, may not always be uniform. So the reporter believes that the opponent can improve his experimental setup by making sure that the size of the ball is relatively small to the handful's closest radius. That's my presentation. Thank you.
Okay, thank you. So now is the time for the viewer to ask questions to the reporter and opponent.
Okay, thank you for the reporter and opponent and the reviewer discussion. And first question, I would like to start with the problem statement. So due to the problem statement mentioned that we have to use a thin wire. So what is the purpose? Because you didn't mention about it.
Concerning to the thin part. So the reason why we should use a thin conductive sphere is because that from calculations we can ignore the radial component here because that the thin electric current caused by this conductive surface can be then ignored.
Okay, I understand. And how about opponent?
Can you repeat your question?
What is the purpose of the thin wire?
What is the purpose of the wire? Since if the wire is really thin, which means that we don't have to consider the mass.
Okay, I understand.
Sorry, I thought you said that.
Sorry, I would like to ask another question about the problem statement. So, why do you use a hollow sphere instead of a solid one?
So sorry, I misunderstood your last question. I was explaining why we use a hollow sphere.
Sorry, I would like to move to the next question. So, why do you use a hollow sphere instead of the?
Like the last answer I answered because I misunderstood.
Okay.
It's because
well, I think it's mainly because when it is not a hollow sphere, then there may be some inner eddy currents that might affect the motion.
Okay. I'm going to move on to the theory. So due to a reporter didn't measure the radius of the coil and the sphere, so
I did measure, but I did not like.
what if the coil radius is smaller than the radius of the sphere? What will happen?
So it provides a non-uniform magnetic field since it will not go through all of the whole sphere.
And how about the distance?
Since I think if the size of the ball is not relatively small to the radius, then the magnetic field the ball experience may not be uniform.
I understand. And did you take the thickness of the ball into the consideration?
Oh, it's 0.1 centimeters.
Okay, so what will be different if we change the thickness of the ball?
Well, if we change the thickness of a ball, we increase the possibility that there might be some inner eddy current that is not on the surface.
Okay, and how about, do you agree with the opponent?
I agree with the opponent since when the radius of the thickness increases, it causes the electric current inside the thickness to increase.
Okay, I understand. And I'm now going to move on to the experiment part. So the reporter mentioned about the size of the material. However, when you change the material, the density will also change, so the mass will also change. Do you think the mass of the...
changes the moment of inertia too.
So do you think the mass will affect your result?
It changes the moment of inertia, so it will affect the
Okay, how about opponent?
Well, changing the inertia, which means you change the tau equals IW, you change the I.
So which kind of result do you think will change?
Yes.
Which kind of result?
Which kind of result?
Yes.
For example, the angular acceleration that the ball experiences.
So you mentioned that damping is caused by the friction.
Sorry, time is up.
Thank you.
Thank you. So following is the preparation time of the reviewer. So, reviewer, please start your review.
Okay, thank you for reporter and opponent and the review of the session. Today I'm going to review question number 2 of the living sphere. So here's the problem statement, and we may focus on a light sphere and white thin. However, the reporter and the opponent didn't mention about what is the purpose of the white thin. So we think that have to be taken into consideration. And then okay, and here's the summary of the reporter's presentation. So they may focus on the effect of the magnetic field and also the magnetic strength in the motion. They mentioned about the friction and also the air resistance. And the theory is that the arc law and the Gauss law and also the eddy current. For the setup part, they use a coil and also the conductive sphere and a thin wire. For the parameters, they said it's about the different material, different magnetic field, and also the induced angle. And for the conclusion, when the magnetic field increases, the damping will decrease, and when the conductivity coefficient increases, the damping will increase too. So here's the pros and cons of the reporter. So they complete quantitative phenomenon explanation and a lot of experiments to prove the assumption. And also I have a good experimental setup that reviewers think is pretty good. And also, however, they didn't measure the ratio between the sphere and the coil. And the concept that makes of the quantitative comparison between the theory and the experiment. And unclear breadth explanation didn't show the experiment for the original damping and could explain the mechanism behind the damping more and didn't measure the radius of the coil, and that's familiar to the research of Mason. So here's the pros and cons of the opponent. The opponent's super polite and calm discussion about with the reporter and also clarify the theory that is misused on the blackboard and also understanding of the reporter's report and clear presentation about his own opinion. And also give some appropriate suggestion about the reporter's report and that reviewer believes that is really appropriate. However, the content that makes of the discussion about the experimental setup and result, we may talk about the theory. So here's the discussion point. So what's the ratio between the radius and the coil of the sphere? However, the reporter answered that they may measure the radius of the sphere, but didn't measure the radius of the coil. The reviewer thinks if the radius of the coil is smaller than the sphere, the magnetic field will not be uniform. And the opponent asked about, can you give a definition of the omega? And the reporter answered that we define as a period. However, a reviewer thinks the definition of omega in the reporter's research is kind of in different forms. And another discussion point is that the opponent asked about how did you make sure the magnetic field is uniform? The reporter answered saying we measured it. And the reviewer thinks the radius of the sphere seems familiar to the radius of the coil. The magnetic field will not actually be uniform. And here's some best points the reviewer would like to mention about. So the first one is that the reporter didn't measure the radius of the coil. So the reporter can make sure the magnetic field they provide is completely uniform. And this is pretty important in this experiment because they use the theory of being uniform. And also, the reporter didn't explain the method they changed the induced angle. And also didn't consider the thickness in the change in the theory. And also, when changed to different material, the momentum of the inertia should be taken into consideration. And however, they didn't consider about the mass when they change different kinds of material. So this is all the presentation of the reviewer. I think, thank you for the reporter and the opponent's discussion part. Thank you.
Okay, thank you. Following is the reviewer makes the remark, please.
Honorable jury's fellow competitors, this is the reporter giving a concluding remark for the previous discussion. First of all, for the theoretical equation of motion is calculated in our theory. However, I do agree with the opponent that the tau equals I alpha bar V is tied into delta. So, however, it does not affect that this understanding for the opponent towards the rotational frequency that you misunderstand. And there are very lines comparing with experiment results in every chart so that we are able to compare with the theory of any deviations. And the direction of any current can be predicted related to the manosphere can be considered in the integration of infinite 2D coils. So for example, today the manosphere is rotating about its vertical axis in a counterclockwise direction. Eddy current on the surface looks like this direction. So we are able to predict the eddy current's direction. And the radius of the Helmholtz coil isn't significant. However, we measured it. But as you can see in our observation video, the radius of the Helmholtz coil is absolutely way much larger than the radius of this part. So as long as it's larger than this radius, then all of the magnetic fields can go through straightly through this ball. And however, the reviewer and the opponent kept saying that it causes a uniform magnetic field that might affect. But from observation video, you can see that the Helmholtz coil is way much larger than this metal ball. And a Hall sphere is used because the thickness of the surface is way much smaller than the radius. Since we mentioned this conductive surface might cause a thin layer of electric current. So when this is thin enough, then the radius, the electric current will be small that we can ignore, which will not affect the main reason of the eddy current that will not affect the average eddy current. And as the size of Helmholtz coil is smaller than the radius, the magnetic field causing the sphere will decrease and slow down the density. Thank you.
So I would like all three presenters stay on the stage and ready to answer the question from the jurors. So any questions? Yeah, please use the microphone.
The reviewer raised an interesting question that is missed by the reviewer. You didn't do the experiments for the size of radius of your sphere and in the field or not. And do you want to comment on what is the size effect on the eddy current and the motion?
So the size is bigger, which means that the cross-sectional area is larger. So the surface for contacting with the magnetic field will increase. So the eddy current on the sphere, if it's larger, then the eddy current will increase. However, the moment of inertia will also increase. So I'm not able to predict, like, if I know the radius or also the moment of inertia, then I can predict how damping is affected or the decay time.
So for the reviewer, could you comment on if it's field or not, and what's your idea on that?
Well, I think the eddy current is vertical to the magnetic field. So could you please ask the question again? Sorry.
If the two spheres have the same conductivity, one is field, one is not field. Just now you were asking him the same question, and what is your comment on that affecting the eddy current and impact on the motion?
Okay, so the eddy current will vertical to the magnetic field, so it will cause a torque that may become the resistance.
How about the opponent? Do you have comment on those questions?
Excuse me, can you restate the question?
I asked the two questions. Do you have comment on either question?
Do you mean the equation that I mentioned?
Sphere that has the same conductivity, one is bigger sphere, one is smaller sphere.
Well, since if we consider the model given in the reporter's presentation that he used a ring, a coil as a commutation to modify the sphere, and I believe that the cross-sectional area will affect the magnetic flux and therefore will change the value of the induced current.
Any further question?
In order to verify that the magnetic field is uniform, you did measure field, right? And the region is it larger than the, say, volume of the sphere? Did you make sure of that?
Which volume is?
The sphere is supposed to be in a uniform magnetic field. And you didn't measure the core radius because you say you just measure the magnetic field to verify that it's uniform, right?
No. We did measure the radius of the Hubble core, but...
No, that's not important. My question is, you measure the magnetic field and make sure they are uniform.
Yes.
And the region of uniformity is larger than the sphere. Is that correct?
Can I explain, like, briefly explain how we measure?
No, my problem
Yes,
is...
that's correct.
Okay.
The question is, did you verify the field around your sphere is uniform?
Oh, yes.
Yes or not?
Yes.
That should settle some problem. But I think the key problem is a very difficult aspect of this problem is the what you call eddy currents and induced angle. You only include, or your derivation only shows the induced currents effects. It provides a let's say
Time B, like
the current is because it's rotating this way, and the current is going like this, so it creates a magnetic field in the y direction. X is the rotation direction, and B is the z direction. And that, of course, is an effect which slows down the rotation. But this second it created a magnetic field in next y direction. Originally, you have a x direction, z direction. This y direction, after being induced, is also in the rotating. It's also in the rotating conductor, right? So it should generate an effect, and that is also an eddy effect, eddy current effect. Is your induced angle related to any of these two? But because I didn't follow your induced angle, what does that mean?
So the induced angle means the angle for, so this is the rotating axis, and the induced angle is the angle between the harmless poles, the magnetic field given through this. So by changing the induced angle, like the same sign B increases. So I also agree that when changing an induced angle, it might cause different eddy currents in different directions. However, we're not able to measure the charge distribution on the sphere.
Okay, I think Professor already got your answer. I think short question, maybe two, 1, 2.
A basic question for all three. How does the damping change the simple harmonic motion?
How does it changes through harmonic motion?
Just change what? What is changed?
What is changed? You mean from different parameters, or?
Simple harmonic motion, you have you can characterize a simple harmonic motion by what? And then what does it change?
You mean how causes the damping?
Yeah, when the damping factor is changing, what is changing in your oscillation?
The K time is how we define that the damping is.
Yeah, sure. We are time is already so short answer.
So the K time is changing.
Okay.
And I believe that the amplitude of the motion will increase due to damping.
That's it. Okay.
I think the simple harmonic motion will acting like the torsion pendulum.
So is that okay? Yeah, please.
So I would like to check what kind of material you use. I mean your metallic bulb. I heard that you use iron.
Yes, but it's actually not like.
Okay, so a short question. If the size is the same, but if you use, for example, iron and copper, do you think there will be a different result?
It depends on the conductivity. So for the smaller conductivity, causes the decay time to increase. So it is more like non-significant.
Okay. Yeah. Further? Okay, thank you. So we move on to the scoring part. Okay, since all the score are already been given, so please show your mark to the reporter. So pronounce, which way I should pronounce it? This way or this way? Okay, I start from my right hand side. It's 6, 7, 8, 9, 9, 6, 8, 7, 7, 7, and 8. And the scores for the opponent, please. 5, 7, 8, 8, 9, 8, 7, 8, 8, 8, and 8. And the scores for the reviewers is 6, 6, 8, 8, 9, 8, 7, 8, 8, 7, and 9. So I would like to ask some short comments. Maybe start from the reporter. We have 2, 9 and 2, 6. Any comments from the 9? E and F.
Somewhere over there.
Yeah, short comment. Reporter, presenter, can you stand up and because the comment is to you.
I think your report is very excellent, and you have a good description of phenomena. I think you quick answer the opponent very short, and when you done this, I think you will get the next score.
Yeah, you want to comment? Well, okay, that's okay. So we have 2, 6. One is from.
For the report, I think there are some key issues that are really.
I don't think it's wrong. The field is not uniform. The only uniform is in the middle part. So your sphere is bigger than the middle surface. So it is not uniform. That is one. And second is that it is a pity that, as a reviewer mentioned, that you didn't measure the natural frequency of oscillating without magnetic field. That is a very big drawback. So that you don't actually know how the damping effect on the oscillations. And also one key point is that is the magnetic field will only induce damping. So could it start the rotation? That you didn't mention anything about that. So I think, actually, on the other hand, you did a lot of experimental work, and the data is really nice, so that you have a little bit average. So that is 6.
Excuse me.
Yeah, please.
I think the uniformity is not necessary in the center. It is almost all the way to where the coil is. Temple's problem. Handhold's magnetic field has this special feature, so that's why it's used very often. It's not just in the center.
Okay. So then for the, yeah, please.
The reason I ask that did you measure the magnetic field and is it uniform? If you did measure it and you make sure that the uniformity covered the whole sphere, then that's it. Of course, the uniformity is not theoretically uniform, but the error should be very small. I think that's the key point in doing this experiment. Other things are not important. The uniformity, you measure it.
Sorry, I think you don't have to. We can just make comments and discuss with the students later. Yeah, because the time is limited. So, okay. For the opponent, we have a single 5 and single 9, 2 7, and a lot of 8. So maybe start from the lowest mark.
Okay. So for the opponent, there are two parts you can perform well. First is for the questions. So it's not a number, but I think the first two questions is too technical, which does not help to clarify the report. For example, you asked about the radius. So that is another thing. And secondly is that during the discussion, actually, I don't see the priority, and also some of your questions wouldn't connect together to help us to understand what actually happens there. For example, you first ask if the magnetic field is in the middle, and then you ask about the material, and very late you ask about the size, but we don't know if all the questions combined. How could that lead to deeper understanding of the topic? Therefore, for these two parts, you got lower grades from me. For example, for the question and ask, you got only 0.7, and for the discussion, you got only 1.5 from me. Otherwise, you should be better.
Okay, we have a 9. You want to comment? If you don't want to comment, we can ask other 8. It's okay. So, any professor giving 8 wants to give some comments? No? Yeah, please.
I think that everyone should know that basically simple harmonic motion is modified by linear reflection, so that it changes temperature and period and omega. I think that they are both spend most of time asking about the omega. In fact, there's a error in the reporters report that omega is proportional to exponential. This would be the antigen proportional. We correct it later, and then we spend too much time asking about these things, and then we regret the subsequent discussion. That's all.
Okay, thank you. So for the reviewer, we have the lowest mark is 2.6, and 1.27, several 8, and 2.9. So would you like to give some comments? You give a 6. Yeah, please.
Actually, for the review, drawback is that you didn't actually review the opposition speech. So otherwise, it's a fair review. And also, additionally, is that the review of the reporter, the report is a little bit too without key points. So you mention everything, but I think here you need to highlight the key points. So basically, otherwise, as I mentioned, it's a fair review.
Okay, we have 9 from Professor Jia. can you give us a short comment?
I'm appreciate there's a female student on the stage. That's the first thing I have to say. And secondly, I think he has a very good strategy plan. Although I agree with Professor Law about his presentation in the beginning, didn't completely cover all the discussion among between the reporter and the opponent. So that's why I give her 9 points. Okay. Thank you.
Thank you. So the first round will close here. We will have a 10 minutes break. So please get back to the seat in 10 minutes, please. Thank you. Please write down the presenter's name on the board. Okay, the preparation time is almost up. So, reporter, please start your report for 12 minutes.
Okay. I
Underwater is below competitors and most teams get. I'm the reporter for Team Brazil. Today I'm going to report the problem number 9, oscillating screw. And for the problem statement, it states that when placed on inside the ramp and released, the screw may experience spring oscillations as it travels down the ramp. And we need to investigate how the motion of the screws, as well as the growth of these oscillations, depends on relevant parameters. And for the phenomenon, first I would like to explain why a screw performs the oscillations on the inclined ramp. And I will simplify the screws consist of the 2 cylinders, and each of them has a different radius. So when the gravity provides the same angular velocity to them, the velocity will be proportional to the radius, so that the bigger path will roll down faster and cause the oscillations. So in conclusion, we can say the oscillations is caused by the tangential velocity difference. And for this page, in the left, we show the decaying oscillations on the 14 degrees of inclined angle. And for the right side, we show the green oscillations on the 15 degrees. And so we can observe that with different inclined angle, the type of oscillations may be different. And for the force analyzed, we can see that there's gravity that acts on the central mass and the normal force provided by the contact point, and also the frictions that cause the rotations. And after analyzing those forces, we can get the degrees of freedom, which will be the position XY and the oscillating angle Z and rotating angle theta 1. And since the screw will rotate during the motions, we need to calculate its moments of inertia. And we assume that the screws consist of the cylinders, so the moments of inertia will be like this. And for the rotation axis along this axis, the rotational inertia will be like this form. And for the acceleration, for the oscillations, the rotational inertia will be this form. And for the normal force, since there is no flipping during the motions, so we can consider the static balance along the z-axis, and by this we can get the value of the normal force like this. And for the analysis of the frictions, first we define the frictions as kinetic frictions because the contact point isn't still during the motion. And the directions of the frictions will be opposite to the instantaneous velocity. So we define the central mass direction vector as S and differentiate with respect to it to get the velocity vector. For the tip part, for the head part and the tip part, we translate the vector from the central mass and also consider the extra tangential velocity caused by rotations. Since the head part will roll down faster, which we have mentioned in the phenomenon part. After we get the direction vector, the frictions can be derived. And after the calculations, we can get the equation of motion by Newton's second law. And for the displacements, we consider the gravity along the x-axis and the component of frictions for both x and y-axis. And for the rotations, we consider the torque that will affect the rotations for both z and y-axis. And for the energy transform, I will use this concept to explain why the different oscillations. When the gravitational potential energy is bigger than the total negative work caused by the frictions, the oscillations will grow. And if the gravitational potential energy isn't big enough, the oscillations will decay. And for my experimental setup, I use protractor for adjusting the inclined angle, and I put the board on the protractor to create the ramp.
And I use tripod for recording. And these are the dimensions I use in the experiments. And for the measurements of the oscillating angle, which will be theta z, I use tracker to track both tip and head part and get their coordinates. Use them and use arc tangents to get this theta z. And to measure the kinetic friction coefficient, I tied up two screws together to make sure there are no extra oscillations. And slide it down from the ramp, track it, and get the VT graph. And use this both to test the acceleration, applying this formula to get the K. And those are the different coefficient of frictions I used in the experiment. And for my first experiment, I changed the incline angle, and will be the 3 degrees, which represent a very small angle, and the 14, 15, 16, and 18 degrees, and also the 30 degrees, which represent a very large angle. And I will use the theta g graph to describe the different types of oscillations. And the control variables in this experiment will be the radius of the head and the length of the screw, but also the surface, which means the kinetic friction coefficient. And in the videos showing on the slide, we can see with different incline angle the screw performs the different oscillations. And for the decaying oscillations cases, in my experiments, from 3 to 14 degrees, the work done by the gravity isn't big enough to let the screws perform the ring oscillations. And we also saw the decay. And we have also run the simulations to compare with our experimental results. And what we get is in the trend of the oscillations, the simulations agree with our experimental result. But there is still roughly 2 degrees difference between the experiments and the theory model, which means we still can, in the simulations, we still can see the decaying oscillations that cause in the 16 degrees of the incline angle. And for the green oscillations, if we add in the incline angle to let it reach the critical angle, it reach in this experiment, it will be the 15 to 16 degrees. And the simulation shows that the critical angle will be the 17 degrees. And if we keep adding the incline angle, the screw will finally start to spin, and its oscillating angle will keep increasing like this. And for the explanations, as the incline angle increases, the gravitational potential energy will also increase, so it will cause the oscillations to grow. And for the next experiments, I changed the length of the screw, which will be the 16, 22, 28, and 35, and 41 millimeters. And I will also use the kinetic graph to describe the oscillation. And for the control variables, which will be the radius of the head and the incline angle, the releasing angle, this should be the 90 degrees. And the surface, which means the coefficient of friction. And we can also see the different oscillations caused by the different length of the screw. And the trend of this it will be as the length of the screw increases, the oscillations will decrease. And that's because as the length increases, the moment of inertia will decrease. Will also increase, which we can see in this formula. And as the torque provided by the gravity will be the constant, so as the moments of inertia increase, the oscillating angle will decrease. And for the last experiment, I changed the friction coefficient to see how different frictions affect the oscillations. The control variables of this experiment will be the length of screw, the inclined angle, and the releasing angle. And we can also see the frictions that will affect the type of oscillations. With the small frictions on the surface, these coefficients will be the 0.3358. The screws start to spin like this. But if we add in the more frictions on the surface, the screws will perform more oscillations on the surface, but the amplitude of it will decay. And for the conclusions, we have mentioned first, as the inclined angle increase, the oscillations will grow because of the gravitational potential increase. And second, as the bend of the screw increase, the moments of inertia will also increase, so that causes the oscillations decrease. And for the last, as the friction coefficient increase, the screw will perform more oscillations, but the oscillations will decrease. That's all my presentation. Thank you for attention.
Okay. Following, we have 2 minutes for opponent to ask questions to the reporter, please.
Okay. So the observation video that shows on the report statement, I think that the growth, the oscillations has decreased, not the growth that the report statement mentioned.
Yes.
So could you tell me how do you define the growth of those oscillations that you mentioned in your statement?
The group of the oscillations, I show that in this slide. And the group of oscillations I define is the head of the angle. The head, the angle the head and tip.
Okay,
relevant to the.
Okay. And the observation video that you showed, which under which circumstance in case 3?
In this situation is the very small inclined angle, so you will just perform the oscillations without sliding.
I would like to ask which inclined angle that you showed in this video.
In this video, I showed is the 3 degrees situation.
And please turn to frame 4. Do you think that the movement of these 2 kinds of the screw is a kind of a damping motion?
Yes.
So as we know, there are some characteristics about the damping motion. So which kind of the damping motion that you think the screw is acting in this system?
In the 40 degrees, you can say that is the underdamping.
And please turn to page 7. Could you tell me which kind of friction is acting as a side view about the screw?
You mean what type of friction?
Yes.
Yes, it is the kinetic friction.
Kinetic friction. Okay, and please turn to page 26.
Sorry, time is up. So, opponent, you have 3 minutes to prepare.
the preparation time is almost up. So, opponent, please take the stage and make presentation for up to 4 minutes, and remaining time will add to the discussion. Please start.
Okay. Honorable jury and fellow competitors, my name is Ethan Shi from Team Epsilon. I'm the opponent today to concluding problem number 9, oscillating screw. For the purpose statement mentioned, I believe that the purpose statement shows the main focus that they are going to focus on the growth of the oscillation and the motion of the screw. And about the growth of the oscillation, I think the reporter shows the different kinds of the oscillation, but the observation video that they show is not growth oscillation. I believe that is a decay of the oscillation. And about the summary of the reporter, and about the theory, the reasons of the oscillations will be because of the tangential velocity differences, and about changing the incline angle to see the influence of the oscillations, and they solve the equation of motion by using different parameters, and about the energy transfer, they find they explain the different kinds of oscillation is because of the energy transfer in the system. And about the part of the experiment, they have the left of the quantitative comparison between the theory and the experiment, and didn't explain the extent of the critical angle, which I believe the reporter can find it more clearly about the critical conditions. And they have less explanation about the theory results. And the analyzed method I suggest the reporter can improve is that they mentioned they use the tracker to track the motion of the head, and in the oscillations, as we know, the angles that are changing over the time was also important. And also mentioned about the oscillations were separated into several kinds. A kind of the oscillation will be the spinning of the screw. Another is the decay of the oscillations, and also the growth of the oscillations, which the purpose statement is mentioned. And about the parameters, they use the incline angle, length of the screw, friction coefficient to do the experiment to prove the equation of motion, and also write the numerical simulation of the equation of motion to do a comparison with their experimental results. And I would like to also mention about the strength and the suggestion for the reporter. About the strength, they have completely quantitative phenomena explanation about the carbon, and they have a lot of experiments to prove the assumption that they provide, and they have well modeling of the screw and have a good experimental setup. And about the suggestions, they have that quantitative comparison between the theory and the explanation. And also, the analyzed method didn't clear explain. And they have didn't define the growth of the oscillations, which I believe is the oscillations about the head, and can clearly describe the observations. And about the discussion for the setup, they measure the friction coefficient. I would like to talk about the friction coefficient about the reporters provide. I would like to ask about which is kinetic or the rolling friction. About the method, the releasing method should also be discussed about that the method they use will take the initial tangential velocity. And about the data analysis, they have the quantitatively found the damping coefficient. I believe it is also important. About data, the angle and the trajectory should be comparative to each other to find the relationship in their oscillation. And about the theory explanation, here are also some parts I would like to discuss, such as the quantitative understanding about the phenomena physics behind, and the concept verification and the quantitative modeling. And I would like to start my discussion now.
Yeah, please.
Okay, let's move back on the purpose statement. So the purpose statement mentioned that you have to investigate about the growth of this oscillation. So did you think you have to investigate about the growth of the oscillations?
Yes, we have done many experiments to check the growth of these oscillations.
About the oscillation. About the oscillations motions, there are some characteristics. Could you tell me some of the characteristics about the oscillations motion?
The oscillation motion, can you define this?
Okay, such as the amplitude of oscillations.
The oscillations will be a periodic motions of the screw.
Yes, I agree to the reporter. The periodic of the oscillation is one of the important parameters that the reporter should be investigate about, and I believe the damping should be also considered in your analysis.
Yes.
And so, in the short question, you mentioned that it is an under damping.
Yes, because there is the constant frictions that cause the damping.
So, could you turn the page that you show your experimental result? I believe it's page 27. Okay, and here's the experiment about the incline angle.
That's the length of the screw.
Length of the screw. So, how do you compare between the different parameters?
I just used the data graph to look the trend of the oscillations and found out that with different length of screw, the type of oscillations will be different.
So you mentioned about your comparison between the amplitude in different lengths of the screw.
Yes.
So do you think that when you increase the length of the screw, that the amplitude should completely be changed since if we simplify it as a pendulum?
Yes.
So the amplitude of the oscillation, that if you choose the length of the screw, the oscillation amplitude should be changed since the initial length of the screw is different.
Yes.
So how do you choose the angle for the length of the experiment?
I choose the incline angle for to let us see the different type of oscillations. Since the incline angle will also change the type of oscillation. So I choose one to let us to see there's the two growing oscillations and three decaying oscillations to make the comparison.
So since the wooden board might not be the equal, would it be a possible factor that made your simulation different to the experimental result?
I mean the wooden board will not be that smooth.
Yes, and in your experimental result, to comparison with your simulation result.
Okay, since we can make sure that the wooden board is every part of the wooden board is will be the frictions will be the same. So in our simulations we can this can be the result for the deviations of the model and our our model.
Okay, and let's look at the simulation result and the experimental result. And let's move on the experimental result here in the 3 degrees. Okay.
Yes.
And in your simulation result about the 3 degrees, the time ended in 3 seconds. So that's your experimental result that we choose the 3 seconds to cut it. And do you think that the periodic of your simulation result and your experimental result can compare with each other?
I think it will also have some deviations.
So could you talk about the possible reason that cause the deviation between the simulation result and your experimental result?
One is maybe the simulations I use cannot completely fit all the situations. And the second one is if we found it in the experience, I think it will be the friction coefficient on the wooden board is at even. So
okay.
Really close.
So which kind of method that you simulate your result?
I use Python to solve the equation of motion.
So recorders, you first solve the equation of motion for the system, and you plug into Python for the numerical simulation result.
Yes.
And so for the simulation of the oscillation system, I think the damping is an important part. So Did you measure the damping about your experimental result and plug into your simulations for the comparison?
The damping for the value of the damping, I didn't measure it in those presentations.
Okay, let's move on. So could you repeat again which kind of damping do you think?
It's the under damping. So it's a constant just across the
Okay, I agree with the reporter. And about the under damping, that we know the equation of the under damping can be written as the equation here. Right?
Maybe you can change another
Okay, so let's just look at the equation. And so,
sorry, I can repeat this equation here.
Okay, I will write the equation again.
Okay.
So this is the equation about the damping.
Yes.
So I suggest the reporter can fit the result as the equation here to find the damping coefficient, and then the reporter can comparison between the different parameters and make sure the damping about the oscillations is differences in different conditions. Changing the length of the screw may also change the initial amplitude about the oscillations.
Yes.
And for another end, when the reporter has the damping coefficient, they can plug into the numerical simulation to make sure that the numerical simulation will get closer to the experiment that the reporter did.
Yes, maybe I will do this in the future.
And could you turn the page that you investigate about the different kinds of oscillations, like the growth oscillations and the decay of the oscillations?
Do you mean this page?
Yes. So how do you make sure that the critical angles go between the 40 degrees and 50 degrees, since that is very similar?
In the experimental result, is quite similar for the shape of the oscillations. So in my experience, I use the protractor to adjust the incline angle, and maybe the incline the exact incline angle is between the 15 and the 16 degree, but I can find it out because due to my setup isn't that.
So do you think the gravitational component in 40 degrees and 50 degrees is similar?
Can you rephrase the question?
Since you mentioned that the reason because the critical angle is of the gravity.
Yes.
Do you think that 40 degrees and 50 degrees has a similar gravity component?
40 and 16.
50 degrees and 50 and 40 degrees.
I think it will be close, but the motion of the screw, I think it will be very sensitive. So if we change 1 degree, the total motions could be different.
Okay, in my opinion, I think the gravitational component in 40 degrees and 50 degrees is very similar. So maybe there is another reason that for the critical angle. So in the theoretical modeling, you have mentioned about the rotation axis of the rod. Could you turn the page of the theoretical modeling? Yes, in this case, do you think the rotation axis is time dependent? Which means will change over the time.
In my model, I assume that is the constant that passes through the central fence.
Okay, thank you, sir. Opponent, please make your 1 minute summary.
Okay, thanks for the answering question about the reporter. In our discussions, we first discussed about the different oscillations in the reporter's report, which is the growth of the oscillations and the decay of the oscillations. and the reporter find the critical angle which will change the different kind of oscillations in their experiment. And about the quantitative comparison with different parameters, I suggest the reporter to use the fitting curve about the underdamping to find the damping coefficient, and they can compare the different parameters by quantitatively. And about the simulations and the experimental results, that there are some of the periods can't compare with each other, so I suggest the reporter can consider more parameters into the simulation to make the simulation result more similar as the experimental results. And here's my summary.
Thank you. So following is the question from the reviewer. Reporter, please.
First, for the reporter, what's the definition of oscillation? The oscillations, I will show that in one presentation that I measure the oscillating angle. I will use the slope to get thank you. And one reason for the oscillation of the screw, because of the tangential velocity difference. Okay, how about components? I agree with the reporter that the tangential velocity was different, and also that the mention about the target. Thank you. The thread reflects the center of the mass. The thread, I think you will not, because the thread is controllable. So you think it won't affect it, it won't cause another weight on the screw. You will cause a weight, but won't change the. And what's the releasing method? What's the releasing method? Releasing method. I use the ruler to release. Like so you use your hand to release. No, I use the ruler. Okay, thank you. And for the opponent, do you think that the ways that the reporter released the screw will cause deviation? I think the method that the reporter released the screw will change the different tangential velocity, which is important about the. Okay, thank you. For the reporter, do you have any theory line in your report? Theory line. I have considered, I've calculated the equation of motion. So you can compare your theory with your experiments? Actually, my simulation is based on my equation of motion. So okay, thank you. So for reporter, when you change the length of a screw, it will also change the mass of a screw at the same time. Yes, and you will represent some of the moments of inertia. Thank you. Please turn to page 9. Page 5. Next page. This page? No, page 9. Oh, page 9. This page. And here, the direction of a friction is parallel, right? Parallel. No, it was, it's the kind of description of the friction. But in the real situation, the direction of friction is not given to it. And for what's the boundary condition of your experiment? The boundary condition. I describe it as the critical angle, and I mentioned it in that. And how about maybe the friction coefficient or the releasing angle? Do you think have a boundary condition? For the yes, I think you have boundary. I think you for the opponent, do you agree with that? I believe that reporter have tried a lot of the vertical angle and critical condition. Okay, thank you. Please turn to page 31. Okay, can you explain why the oscillation at this is
time is up.
Okay, thank you.
So following is the preparation time for the reviewer. reviewer, please make your review.
I'm the reviewer from Team 7. Today I'm going to review problem number 9 of the leading screw. And here's the final statement. When placed on its side on a rim and release it, a screw may experience pulling oscillations as it travels down the rim. Investigate how the motion of a screw as well as the growth of these oscillations depends on relevant parameters. And I'm going to mainly focus on when will the screw experience pulling oscillations and how will relevant parameters that will affect the oscillation of the screw. And here's a review of the reporter. First, in the phenomenon part, they have shown about the oscillation of screw, and in the theory, they have talked about the equation of motion and also the energy transformation. And they have done the experiment about different parameters like the inclination angle, length of the screw, and also the friction coefficient. That's the conclusion. And I think the reporter here great job demonstrated the phenomenon about the oscillation of the screw, and also he has shown the clear experimental diagram, and also I think they have a very clear theoretical model, but the primary condition isn't considered in their report, and also they have a low comparison with the theory, and also I think the explanation of overturning is the explanation of overturning is too little, and also the detailed mention about releasing method. And here's a review of the opponent. I think he did a great job discuss about assumption, and also he has clearly understand about the reporter theory, and also he has pointed out reporter experiment error in her theory part and also experiment part. But I think he didn't go well about discussion the boundary condition of the phenomenon that the oscillation of screw, and also he didn't mention about the physics behind different parameters, and he also didn't mention about the energy transformation when the potential energy decrease. And here's the discussion part. The opponent asks, how do you consider a characteristic of a screw? The reporter answered, we didn't compare the amplitude of the oscillations. And the reviewer thinks that we believe that we should investigate on amplitude for the maximum angle and the acceleration in y-axis, angular acceleration. And the opponent asks, what caused the deviation in your experiment? The reporter answered that error parts come from the wooden rim surface, and the reviewer believes that it might be caused by the initial condition for the releasing method, and I suggest that they're using an electromagnet for the releasing. And I asked about the reporter and opponent. Is the direction of friction parallel in the two different contact points? The reporter answered no, and also the opponent would agree with the reporter, and I also agree because the velocity on the different contact point is different, so of course the friction is not parallel on different contact points. And I also asked will the drag affect the contact points or change the location of center of mass, and the reporter says no, it will not, and also the opponent agreed with it, and I also agree. And here are some points about the discussion. First, I think the reporter didn't define the sliding and the oscillating clearly, and also in the theory part, I think it didn't have explain more about energy transition, and also the opponent didn't discuss it about it more, and also the difference of two contact points. And I think that when the reporter changed the length of a screw, it also changed the mass of the screw. So I think it should be controlled. And also about the deviation analysis, I think he can explain more.
The time is up. Following is the time for a reporter to make a concluding remark, please.
Okay, I'm going to conclude my presentation. First, I would like to thank for the opponent and the reviewer for such a pleasant discussion. And in the discussions, we have talked about the definition of screw oscillation and the kind of friction will be the kind of friction, and also the damping. We can the opponent suggests us can measure the damping to make our simulations more completely. And the rotation axis, we'll also talk about the rotation axis will change over time. And the reporter thinks that in your model, we just assume that it's is fixed to the pass-through central mass. But in the in the another situations like it starts to spin or like reverses is overturning, the axis of it will I think it will change. And for the fixes, we agree with the opponents that we can do more parameters in the experiment to measure the more boundary conditions. And we can try to use different releasing methods is because although we try our best to not that the releasing methods to change our result, but I think it will slightly have some deviations from our results. And for the page 31, the graph on the left-hand side, which we reverse as mentioned, it is performing the spinning. And finally, I want to talk about the energy. Why I don't use the energy transform to analyze the motions. That's because that if we need to calculate the friction, we need to calculate the total path of it, and it's very complex to calculate it. So I just use the initial motion for simulation. Thank you for listening.
Then we move on to, I would ask the three presenters stay on the stage, and the jurors, you can ask questions. Any questions? Yeah, please. Yeah.
Okay, I would like to ask the reporter, you changed several parameters, but can you fix the length of the screw and by changing some parameters that you can observe some differences in the oscillation period?
Meaning the period will be different.
For example, maybe you can, for a screw, there are different threads. Yeah. For the different threads, I think that the friction and also the torque also influence your results.
In my experiment, I didn't try the use different threads to do the experiments, but I think.
I think that's okay. You didn't change.
So how about you?
I think to fix the error about the length of the screw, you can make the reporter can use the damping analysis to find the damping coefficient, to compare with the different parameters, or found the period of frequency. The reporter had mentioned about the screw oscillating because of the center of mass is not in the middle of the screw. So I think when he changed the length of the screw, he also changed the length.
Okay, thank you. So more specific, if I fix the length but I change the thread, what will happen?
I think it depends on how the parameters will affect the center of mass. And in the video that the reporter provided, you can see that the screw is not falling in the vertically. So I think changing the thread will changing the trajectory of the falling on the rest.
Thank you.
So how about when we change the length?
Fix the length.
Fix the length, but the threads change.
So we fix the length of the threads will change, and the thread will, the amount of stretch will, maybe it will change the mass of the screw, so that causes the center of mass to, the position of the center of mass change.
Okay, thank you.
So if there are no further questions, oh yeah, please.
The reporter, what kind of friction are you assuming for your simulation? Does it depend on velocity, or it is independent of velocity?
Okay, in my experience, I assume that the friction is the kind of friction. But in the several conditions, like in the previous, in the phenomenon part, I showed the oscillations without sliding, and
in that situation.
Well, my question is, what kind of friction do you assume? Does it depend on velocity or not?
That will depend on the sliding velocity. If there are no sliding velocity, the screws will perform the pure rolling. So
the question is the friction you consider is a function of the speed or not?
It's not the function of the speed.
So it's just a constant, independent of velocity?
Yes.
Okay. And in such a case, do you think the term under damping or over damping still apply? This is a question for all the three companies.
I will reply to this question. I think that that kind of damping would be the under damping, since I assume that the friction is a constant.
So you say that the friction is in the cause of the damping?
Yes.
Okay.
Okay. And the opponent?
About the damping, I think the head of the screw will move back and forth at a point, so I think it is a kind of under damping.
Okay.
I think because it's rotational, so it's under damping.
Okay.
Okay, so, a short question, please.
I have a question for both three teams as about energy. So you talk when the scrolling, so which means that the oscillation energy is growing, but simultaneously it is sliding down, which means that the kinetic energy is growing. So does it violate the conservation of energy? So let's start from the reviewer. Reviewer first, and then reporter, and finally opponent.
I think when the screw is
reviewer first.
When it's oscillating, and the potential energy will change to the rotational energy and the translational energy. And because the rotational energy will cause the friction, it's like the energy dissipation, and so that the rotation and
please short answer.
Okay. Energy. The potential energy turns to the rotational energy and the rotational energy.
Okay.
Translational energy.
For my analyze, the gravitational potential energy will provide the whole energy for the sliding and oscillating and rotating. Also, the energy will be taken because of the frictions. So the jury just mentioned that when the screw is sliding down, the free oscillations will be there.
Okay.
So I think the potential energy will transfer into the three parts of the kinetic energy, which is the rotation energy, oscillating energy, and the sliding kinetic energy in the system. And I think the energy will decrease because of the friction, but we have to find a trajectory of the friction to make sure how it works on the system.
Okay, so I think we move on to the scoring part. Okay, it seems all the scores are ready. So we start from the reporter. Please show your scores. It's 5, 7, 7, 6, 8, 6, 7, 8, 6, 7, and 7. The scores for the opponent, please. It's 5, 8, 8, 8, 8, 7, 7, 6, 7, 8, and 7. And the scores for the reviewer. There are 6, 8, 7, 8, 8, 8, 7, 7, 7, 8, and 9. So we need see some comments from the high and the low scores. And if we have more time, we would like to ask some comments from other jurors. So for the reporter, we have 5, 3, 6, 0, 7, and 2, 8. So we start from the 5, please.
Okay, for the report, basically the lower grades comes from the science communication. So you did basically you have good mark. Basically you have good experiment, but when you talk about your results, you just say that this is the formula and that. And also for we didn't introduce the coordinate system. Where is the x and y? Is it on the sliding plane or is it in the laboratory? Usually the flat plane and so on. And such that we cannot understand what happens really there. And that is one. And secondly is that for your comparison between your experiment and simulation, we couldn't directly see what happens between the two. So it is hard to follow the results and to understand all the ideas that you bring us. So that is the big drawback here.
Okay, so how about the 8, Professor Pomikon? Would you like to comment?
I think overall the experiment shows that three different phases: decaying, growing, and just flipping. I think that is quite interesting to see these effects. But I think I just give 8 because I should give better marks, but we ignore the XY direction. What happens in this case, how the XY changes, because the motion along the plane will affect the motion of rotation. I think we should put this correlation together, and then we can get better marks.
Okay, thank you. So for the opponent, we have a 5, 1, 6, 0, 7, and 8. So we start from the 5.
So for the opponent, the very bad point is that you didn't discuss anything during the 10-minute discussion. So you just play around and ask questions, but never go into any physics. That is very bad. And secondly, for the questions asked, so you almost focused many on. So never that did not help to clarify anything. So that I gave you overall 5.
So for the opponent, you want to give some comment?
I give opponent 8 because I think the presenter is very good at carrying out the discussions, and that was very good to understand the details.
Okay, thank you. So for the reviewer, we have a 1, 6, 1, 9, and equally 7 and 8. So start from the 6.
So for the review, actually, basically for the questions and ask, questions part, there are one type of them are concentrating on technical stuff, and also for these questions, you didn't go into details during your concerning which therefore so a little bit as I mentioned, so normally it's peer review, but on peer review 7, so from that you lower grades from me, that is.
So any further comments?
Yeah, I give 9. Apparently, not because he is the male student on the stage. Okay. I think he asked some questions I also want to ask. For example, the initial condition, the contact points, and also related to the moment of inertia. And those factors are also very, very important in the discussion. Although the time is limited, he didn't go into the detail. However, I think he still did a very good job to point out those points. Thank you.
Okay, thank you. So since there are no further comments, okay, so I would like to close this round and take a 10 minutes break. So please come back to the seat in 10 minutes. Thank you. I think the time it's time to start the last round of the final fight. And since everybody is on their seat, so I would like to start the final round of the final fight. The reporter will be Upsilon, and the opponent will be Excel Fire, and the reviewer is Galileo. The problem to be presented is serum. So you have 5 minutes to prepare, and you can start whenever you are ready. During the preparation time, please, all teams, write down the presenter's name on the board. Okay, the time is almost up. The reporter, please start your report of 12 minutes.
Viewers and fellow competitors, I'm a reporter from Team Israel. Today I'm going to report problem number 3, Siren. Here's my problem statement. When you direct an airflow through the rotating liquid hole, you may hear the sound. In this video, you can see the experiment demonstration, and the black beam is needle wheel, which can produce an airflow. For our main focus, I will have the spectrum analyze the sound characteristics, including amplitude and frequency. For the experiment, I will have such relevant parameters like amount of the host, location of host, rotational speed, and size of the host. Here's my outline. For theory, I will have a simple model to show my concept more clearly. And we're going to discuss 3 main things: compression wave, harmonic, and expanded spatial frequency to Fourier cosine series. And then for my experiment, I will import a wrapper into Python and then conduct FFT figure by changing this parameter. And finally, I will have a conclusion and reference. Then let's move on to the theory. As the dynamic diagram shows, you can see the air molecules vibrate behind the disk, and it's the reason that causes a compression wave. And then you can turn your compression wave to by Fourier transform turn by time domain to frequency domain. And after this level knowledge, we can define the harmonic. So we assume the fundamental frequency will be F, and the harmonic will be multiple related. And you can find arrange a series of frequency on the frequency domain. And then for a compression wave, you can know the stream of air that comes out of the host are trapped by the moving disk. Air vibration causes compression wave, which makes the sound. A little console simulation, like your wing vibrates behind the disk, it will have a vortex on it. And the upper one will be the pressure, and the lower one will be the velocity of your simulation. And these two simulations will show different rotational speed simulation. And the left-hand side will be when you spin your disk, and you can see the vortex on you will be not the constant, but when the disk will spin, the vortex will be constant. And next, we need to define the spatial frequency. So we can look at A of X to be the intersection area of the airflow in the hole, and its waveform will be a series of torsions. Then after this concept, you can frequency equal to rotational speed and times the amount of holes, and amplitude is related to A of X, which means the area common to the frequency common to the hole in the pipe. And next will be my equation derivation. So first, we define A of X to be an intersection area of the M and the hole. And the L means distance between adjacent holes, and air source means center to hole center. And A means radius of the hole. The real line circle will be the host on the disk, and the dotted line circle will be your air source. And the black area will be the A of X, which is equal to A of minus X and A of L minus X. Since the fundamental period is 1 over L. And then we can write down A of X into Fourier series. And geometry gives this equation through some mathematical calculation. And thus, the Fourier component A will become by this equation. And then we can divide D equal to 2 pi NA over L, and we divide S of D function. And the right figure on the corner will show a relationship between S of D and D value. And there will be a reminder up there, then you see the relationship below. And finally, we can compute the n harmonic and get this equation. The S of function will be relative intensity, and cosine power will be natural frequency. Finally, we can get the fundamental mode, which means the Ft equal to Q times R. Q means amount of holes, and R means the revolution per second. And I'm going to discuss Fourier transform again, that every complex wave can be decomposed to superposition of multiple side waves. So use the four versions both to analyze your sound. And next, let's walk through the experiment. Here will be my experiment setup. For left, you can see a main stereo instrument. It consists of a disc and motor. And for the air source, you can see the air pump and hose on it, and which can make sure you have the steady flow. And for space, I will use the acoustic echo to make a sound absorbing box to decline the reflection in your space and sound distortion. And for rotational speed, I use the sensor Arduino to make sure. And recording, I use deduction microphone, because if you use the cell phone or maybe some device to record, you will have a sound distortion, and that will affect your result. And for drilling, I will have a drill and drilling machine. And below will show my space improvement process, from a small band to controllable side motor, and finally adding sound absorbing box. And for a program, I will use the Audacity and Python analysis. And this schematic will show my experiment parameters. Small Q means amount of holes, and small R means hole distance, which means the hole center to the CD center. And big R means rotational speed, and small m means hole diameter. In experiment 1, we try to train different amounts of holes, which means Q to 4, 6, 8, 10, and fix the other parameters. And in this spectrum, the experiment result will become 145 Hz, and there will be the harmonic behind it. But the sound we hear will be the fundamental, and the theoretical model with prediction was 132 Hz. And this quite match our theory and the experiment results. And for 6-hole situation, the experiment result will be 205 Hz. And 8-hole situation, it will become 270 Hz. And 10-hole situation, the result will be 325 Hz. So based on this result and the theory I previously mentioned, we can know as the amount of increases, the frequency will be higher. And the figure will show the comparison between theory and experiment. And they will have the error bar on it because I do all my experiment for 50 times. And for experiment 2, I try to choose different location of holes, which means more R, and fix the other parameters. And we can see in 3 centimeter situation, which means the inner ring, the experiment result will be 260 Hz. And 4 centimeter situation, which means middle ring, the experiment result will be 254 Hz. And in 5 cm situation, which means the outer ring, the experiment result will be 258 Hz. And based on these results and the theory I previously mentioned, we can know as the hole distance increase, it won't affect the frequency. However, it makes the sound louder. And let's still will have a comparison between the theory and experiment. And in experiment 3, I try to train different rotational speed, which means big R, and fix the other parameters. And we can see the fundamental still will be the 124 Hz, which still pretty match our prediction. The theoretical model will be 104 Hz. And in 26 RPS situation, the experiment result will be 199 Hz. And in 33 RPS situation, the experiment result will be 264 Hz. And 65 RPS, the result will be 505 Hz. And 91 RPS, the result will become 704 Hz. So based on these results, we can know as the rotational speed rises, the frequency will become higher. In experiment 4, we try to choose different hole diameter and fix the other parameters. And we can see that the experiment result will be 260 Hz in 3 mm situations. And in 5 mm situation, which I let the hole get big, the experiment result will become 260 Hz. And 7 mm, the result will either the 260 Hz. And based on these results, we can know as the hole diameter gets bigger, it won't affect the frequency. However, it does make the sound louder. And finally, I will go into my conclusion. There was some key parameter between the frequency, amplitude, and different parameters. That's the frequency related to n harmonic, amount of pulse, which means small q, rotational speed, which means big R, and amplitude is related to n harmonic, amount of pulse, which means small q, location of pulse, which means small r, and hole diameter. And there will be reminder function down there. For conclusion, we can know in experiment 1, we try to show different amount of pulse, and we can know as the amount of pulse increases, the frequency will be higher. In experiment 2, we change different location of pulse, we can guess as the amount of pulse distance rises, the sound will be louder. And in experiment 3, we can know we can change the rotational speed, and we can know as rotational speed rises, the frequency will become higher. And in experiment 4, we change different hole diameter. We can know as the hole diameter gets bigger, the sound will be louder. And below will show the comparison between theory and experiment, and they will have the error bar on it. And there will be my reference paper listing.
Please ask your question. Have you measured that the speed and its content?
You mean the
speed that the disk spins?
No, if I change the voltage, it would be changed.
Okay, I'll skip to the next question. Have you tested the speed of the airflow?
No, I didn't.
Okay, next question. Are there any boundary conditions of this phenomenon?
Boundary conditions? I think I don't know.
No boundary conditions. Okay. Have you measured that nozzle is perpendicular to the hose?
Can you repeat your question?
Have you measured that the nozzle is perpendicular to the hose? Okay.
Yes.
Yes. Okay. May I ask you on page 35? Ask another question first. Do you consider resonance in your experiment?
No, I didn't consider resonance in my experiment because there will be a hole on this, and they will
take a page 25. What do you mean when a unit is AU? Does it mean the distance between the Earth and the Sun?
Just nice.
Okay. Do you measure the effectiveness of the sound-absorbing box in your setup? Okay, next. Do you consider the area change of the hose between the nozzle?
Yes, I consider it.
Okay. Will there be a sound that cannot be heard by human ears?
Yes.
And do you measure natural frequency of the disc?
Yes.
Did you calculate about the Reynolds number in your experiments?
No.
No calculation. Okay, my progress is up to you.
Okay, thank you. Now it's time for preparation. 3 minutes.
So it's time for the opponent to make 4 minutes presentation. Please start.
Honorable juries and fellow competitors, as the opponent from Team Excel here, then I'm going to oppose problem number 3, Cyril. Problem statement: if you direct an airflow onto a rotating disc with pulse, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on the relevant parameters. And we'll mainly focus on the origin of the sound and how do different parameters affect the characteristic of the sound. This is the reporter's outline. In the theory part, they introduce the frequency under different parameters and the intensity. They use strength units to analyze the amplitude of the sound. So I'll discuss this later. They still have the relative intensity of each harmonic, and they use Fourier series to extend the frequency recorded from the sound. For the experiment part, the parameters that analysis include the Hall numbers, angular velocity, size arrangement of the Hall, and the size rate of the width, nozzle, and Hall. However, they lack of error analysis because they lack of error analysis since there are lots of deviations and error bars in their experiment. So I think I can improve in this part. These are the strengths and weak points. We believe that the trend fit this theory. However, there are still some deviations, and they have clear phenomenological explanation, so we can understand how the phenomenon actually occurred. They have complete factors such as the location of the host and the interval between the hosts. They have done complete math calculation to prove that these arrangements should not be ignored. However, they ignore a lot of factors such as they cannot prove how it affects the result about the arrangement, size of the host, and wind nozzle. And they cannot explain how frequency the charts. The precision sink from frequency deviation well. They lack of the basic insight from the math calculation. They have no physical reason why the location of the host affect the intensity of the sound. These are the points the opponent wants to discuss. About the origin of the sound, we want to discuss why is the longitude wave formed by the air particles. And they have shown that the fast Fourier transformation and show the fundamental and overtone frequency. However, there are some errors parts I want to discuss. About the parameters, we'll mainly focus on the wind speed. Since that the reporter focused on the intensity of the speed, however, they cannot quantify the speed of the wind because we think that it is related to the intensity. So we will discuss it later about how do they change the parameters. For the prediction of the characteristics of sound, we will talk about the relative intensity of each harmonic. And they still have many unexpected peaks in their graph. So we want to discuss where the deviation comes from and the size of the host, frequency of the width of the disk affect this deviation. And I'd like to skip to the next part.
Please get on the stage and we start the discussion.
First, can you verbally explain why the phenomenon occurred? Yes, verbally.
The sound occurs because the air vibration, which causes the compression wave, and you can hear the sound.
So there's a compression wave between after the hole, so there we can hear a sound.
Yes.
So do you agree that a sound wave is a stationary wave?
Stationary wave, can you clarify your question?
Means that the wave does that it doesn't move in the direction.
No, I think that the origin of the sound just when you never be the speed, and when the airflow pass through, and then when the CD rotates, the airflow will be cut into many segments. So when you have the compression wave there, and maybe you will like this, and when you have the three segments, so which cause the vapor
from the sound that we can hear through our ears. Okay?
Yes.
Would you agree that the turning speed of the disc will affect the particles of arrangement of the layer and affect the sound?
Yes, the rotational speed will affect the frequency of the effect. Frequency.
Like the tendency. The opponent believes that when it rotates faster, the frequency will be higher.
Yes, the rotational.
Okay, do you agree that the number of holes affect the result?
Yes, the number of holes will affect the result.
Just like the result of angular velocity, right?
Yes.
Okay. Do you agree that since I think it's page 18, you have a calculation of the nozzle and the area of the hose. Okay. You draw this chart, right?
Okay, can you show in my presentation?
I think it's page 8. Yes. You draw the area comparison between the hose and the nozzle. Yes, like this. So this is the peak when the nozzle completely is over the hose, right? Yes. And since you change the size of the hose, so with the nozzle, this is the nozzle. When the nozzle is smaller than the hose, do you agree that on the amplitude of the wave, there should be like changing to like this?
Yes, so since we have shown my waveform, well, it will similar to the motion.
So do you consider this factor when you draw when you do the experiments about the size of the hose?
Yes, I have done it in my size of hole, or that's the one of the parameters in my experiment.
Page 25. Since that you use units called AQ in your experiments, why don't you use a more direct units such as decibels so that we can understand the amplitude means?
Because that can clearly describe your ratio between each amplitude.
So give me an adverb. Can you please describe what clearly means? Does it have any physical insights between the units?
Because this picture just want to show the intensity between each harmonic.
So you just want to show the intensity. So the opponent means that if you want to show the intensity, you can use decibel, this unit, to more directly express how the sound intensity.
No, but in the reporter view, I think the AUD, just use the AUD can be clearly describe the intensity between each harmonic.
Okay, next question. Page 10 to page 25, yes. And it seems that there are some unexpected peaks at the end of the chart. Can you explain why it exists?
Yes, I think that maybe will be some white noise or some reflection in your face.
White noise. So do you agree that this part of arrow can be explained by white noise? This part, white noise. You think this is white noise?
Yes.
These are white noise. Okay. So do you agree that there will be specific? Can you please don't change? Do you agree that there will be originally there will be some peaks? So yes. You believe that there will be peaks in the white noise?
Yes, there will be peaks in my.
This part, the opponent disagree this because with the parts because there shouldn't be a significant sound peaks in white noise.
Yes, but the intensity of it will be lower, so you should not consider the white noise.
There is a significant peak at the deviation part, so we believe that there must be some other parameters that will affect the peaks.
So now what affect the peak as you share things? Could you understand the problem statement? That the problem statement should say if you direct an air flow, that's the way.
I think that there must be some other parameters that will affect the unexpected peaks parts. So when you draw this chart, let's draw another state. So at one moment it passes the hole like this, and the next moment it will passes like here. Okay, yes, you agree? And at this moment it will be higher intensity of the air at here, right? Yes, and here will be lower, and the next moment it will be like here. And it's higher density, lower density. So I believe that it is the carbon vortex street that will cause some unexpected peaks at the end of the.
I didn't show the vortex concept in my presentation, so can you explain it?
You just agree with the carbon vortex part.
No, I just agree with the compression wave part, not the vortex part.
This compression wave we call it the carbon vortex street, and
the opponent believes that it is the main reason that causes unexpected peaks. So did you know what I measured in my experiment? It doesn't depend on whether you showed on your peaks or not. It is the physical phenomenon that whether it is problem. Yes, I agree with of your point, but that wouldn't affect my result of the calculation. Let's get the next part. Page 37. Okay. When you draw the intensity of the charge, yes, we believe that there should be a fundamental amplitude and several origin frequencies, right? Yes. And it seems that page 35 or 37, I think. It seems that there are also some unexpected peaks at the initial part of the chart. Can you explain why? Yes, that would be the motor, maybe like a motor, and I put it in my backup page. You can directly explain to me. I can listen to you. As this picture, you can see the motor noise, and I analyzed it, and you can see the fundamental will become significant. You did not delete the extra noise produced by the motor. Yes, I didn't delete it, but because that wouldn't affect the frequency that we measure. You superposition the noise from the motor and the sound from the phenomenon. So the opponent believes that there should be some method to delete the. Yes, there should be some method. There should be some method, but that didn't matter our result. Because our result wouldn't be the intensity of it wouldn't be higher than our experimental result than the fundamental frequency. For next part, we'll talk about the intensity of the sound. Can you explain why? Do you stabilize the intensity of do you stabilize the speed of the airflow from the nozzle you provide air? No, I didn't. You didn't stabilize. Oh yes, I used. You didn't stabilize. So I don't believe. No, I didn't. Yeah, I understand what you're asking. Can you repeat this? The nozzle will provide the air to the hose, right? Yes. Do you stabilize the speed of the airflow from the nozzle? Yes. Have you tested it? The number, the speed. I didn't test it because that was the thing that no, you can just test it we're not doing the experiment. So I don't believe that if the recorder should test the speed of the airflow to measure that the intensity from the intensity of their sound is.
Sorry, you are talking to the audience, so you want to make the conclusion. If not, please do discussion between you two, not to the audience. Okay, please.
Can you say why you want to test maybe your speed of your air source? When you want to draw the graph that's measure the intensity of the sound, you have to measure that the speed of the speed of. Yes, I agree with you that the intensity of sound will be affect your speed of your air source, but it won't affect the frequency. So do you measure that as constant? Yes, that's a constant because in my experiment setup, the air source will be the steady force I previously mentioned. Okay, I think my discussion is up to you.
Okay, following will be the summary of the discussion by opponent, please.
This is the discussion summary from the opponent. First, we believe that on your setup, they didn't measure that the nozzle and the hose perpendicular, so that there might be some extra peaks in the intensity chart. And the origin of the sound comes from the interaction of airflow, so that it forms refraction and consumption. The pressure between the wave will make the sound. And the factor that should be considered, including the wind speed, they should have measured the exact amount, the number of the speed should be considered. And this coincides for the unit AU, and we suggest that using decibels so that we can directly understand how the intensity means. And for error analysis part, we believe that white noise doesn't have significant peaks, so there must be some extra parameters that affect the result. Thank you.
Okay, thank you. Now is the time for reviewer to ask questions to reporter and opponent.
Okay, so thanks to reporter and opponent. First question I want to ask, so is the air source a steady flow?
Yes.
Okay, thank you. So if it is not a steady flow, what will change? Maybe the frequency or amplitude?
Frequency and amplitude will both change.
Will both change. Okay, thank you. And next I want to ask the reporter, so did your CD vibrate while rotating?
Yes.
And what do you think will it affect the results? Yes, the CD vibrates while rotating.
The vibration of CD, yes. I think will definitely affect the results.
Okay, thank you. And next I want to ask the opponent, since you mentioned a boundary condition in your question, what will it be?
I mean that when the steady speed of the disk is too slow or too fast,
Too slow, too fast.
possibly will not
Won't hear the sound. Okay, thank you. So do the reporter agree?
Yes, I agree.
Okay, thank you. And next I want to ask the opponent, it is a standing wave of the sound.
Standing wave?
Because you mentioned the standing wave you draw on the whiteboard.
I would believe that it is.
No,
I don't believe that the standing wave of the sound because
So you think it is a compression wave?
Yes.
Okay, thank you. Next, I want to ask that, do you think that the white noise should be deleted in your results?
No,
it shouldn't be deleted. And what do you think?
I think just like the motor arrow.
Yes. So should the motor arrow be deleted in the results? What do you think? Should be deleted. And what do the reporters think?
No, I think that's what.
Okay, so in my opinion, I also think it shouldn't be deleted since you can still get the fundamental frequency. And next I want to ask that, so the reporter agreed that the opponent used common border streets to explain the result. You didn't agree, okay. Next I want to ask that, what will be the main parameter that change the frequency to the reporter?
It's rotational speed and the amount of the host.
And I want to ask, what is the main parameter that change the amplitude in this experiment?
With speed, because it contains more kinetic energy.
Okay, thank you. So, what do you think that if since I have asked the opponent that if the air flow is not steady, what will it affect the results?
If the air flow will not steady, I think that will affect the amplitude. Yes, but I didn't consider it because we have a steady.
Okay, thank you. So, what if the hole on the disk is too big? What will change?
When the host gets bigger, the amplitude of it will become larger because you will get the.
So the amplitude will become bigger.
Yes, the compression will become bigger.
Okay, and do you agree?
I believe that the frequency will change since I draw the chart on U wave.
Okay, thank you. So what if the thickness of the disk change? What will it affect the results?
Because the distance is the air can react and the distance becomes longer, so the stationary wave, the frequency will change.
Okay, thank you.
Okay, thank you. Now is the time for reviewer to prepare. Yeah, reviewer, please present your.
Okay, thanks for discussion between the reporter and opponent. So, I'm the report reviewer from Tinkerville and going to review topic number 3, siren. So this is the problem statement. That's when you direct an aerosol into a rotating fixed hose, and you make hear the sound. So in this problem, the report's main focus will be the sound characteristics and relevant parameters. And so here's some summary and comments for a reporter. For theory parts, the reporter uses Fourier transform for time domain to frequency domain, and also harmonic motion and compression wave. That's how we can perceive the sound, and also spatial frequency. And so for experiment, the reporter used tools like motor, disc, rotating speed sensor, pulse and air pump, sound absorbing box, console simulation, and the direction microphone. And for parameters, he changed the amount of pulse, rotational speed, and hole diameter. So here's the reporter's conclusion. When the amount of pulse increase, the frequency increase. The location of pulse, if changed, it will affect the frequency by amplitude. The faster rotational speed is, the higher sound frequency is. When the diameter of the pulse increases, the sound will be louder. So here's some of my comments for a reporter. That his presentation has simulation for comparison, provide a measure for observe the environmental noise, and comparison between theoretical results and experimental results. And also can use FFT and STFT to analyze the sound. But some of my suggestion will be that maybe he can have more explanation behind the analysis through Fourier transform. So here's some of my comments for opponents. For advantage, I think he has discussion for the experimental data and also a lot of parameters. And also can ask about the graph and the results that the report is shown. But some of my suggestion will be that maybe he didn't organize the questions and also can sum up the short conclusions during the discussion. And also that is also very hard to understand the questions and also fail to understand some aspects of presentation. So here's a review for the discussion. First question is will there be boundary conditions since the opponent has mentioned that the reporter has no obvious comments, and my point of view will be that opponent should specify the definition of boundary condition. The second question is can you explain the phenomenon? Reporter says it's because of compression wave, which I think originally stated in the presentation agree with the reporter. The third question is sound wave a standing wave? The reporter says no. My point is the compression wave should be traveling. The first question is will a number of pulse affect? The reporter says yes. It was clarified stated in the presentation, and there are relevant experiments and results. The first question is, how did you use Fourier transform? The reporter said to separate references. My point is that it would be great if opponents can provide a better way. And the second question is, do you agree that the uncommon vortex tree is the reason? The reporter said no, which I think it is stated in the presentation that compression wave is the main cause. The eighth question is, how did you eliminate the sound caused by the motor? And the reporter said it won't affect. Our point is how we believe the reporter put the device in a box that absorbs the environmental noise. So here's some of my questions. First, is it a steady flow if no one will change? The reporter said that it is a steady flow, and the opponent said that if it is not steady flow, it will affect the frequency. The second question is, was there a vibration in the CD? And the reporter said no, and also asked the opponent that the vibration will affect the result. The third question is, it is a standing wave. The reporter said no, it is a compression wave that affects the result. That we can hear the sound, but the opponent said yes. The first question is, do you agree with the explanation provided by the opponent? And the reporter says no. The first question is, what are the main parameters that change the result? The reporter says that host and angular speed. And so when the hosts are bigger, the compression wave will get bigger. Okay, thank you. This is my presentation.
Thank you. So now is the reporter to make the concluding remarks for 2 minutes, please.
For review and opponent, and first I want to restate the factor of whether affect our result. Since the problem statement just mentioned direct and airflow, so in reporter view, the frequency we should measure will be the airflow instead of the wind. Since it's just a factor, but would affect my result. And then we measure some white noise, and we can see that the frequency of motor wouldn't affect the result. And next in my experiment, we can see the frequency that we often would locate at maybe about 100 to 700 hertz. So which means the smaller frequency, so that the only will change will be the waveform, which I mean temporary accuracy. So according to this reason, I surely believe we didn't need to consider it in our results, maybe Bohr-Action Reynolds number. And there will be some highlights in your discussion. For problem statement, they will state the sound characteristic and frequency and amplitude. So we figure out the reason of sound produced and use this sound as a reference to avoid the reflect sound and sound distortion. And analyze the different frequency components by NFT spectrum and some of the experiment to figure out the theory is correct. And for concluding remark, there will be a fixed point. Rotation speed of the disc is constant, and the dB will be the same meaning as amplitude in Fourier version. For that, I can agree the opponent say wouldn't use the other design. And we control the speed of air to make sure the effect of frequency can be ignored. And we think the motor sound that don't affect the result shouldn't be in this, or maybe the result will be distortion for this process. So I wouldn't delete it. And some of the assumptions that the opponent mentioned are not in your cases. And finally, maybe opponent could tell us under what situation that we could not do error analysis since we think our results are unified or clear. And that's all of my presentation. Thank you for listening.
Okay, thank you. So I would like to ask all three presenters stay on the stage, and we move on to the question from the jurors. Any question, please?
Sorry. At the beginning, I would like to ask if you ever calibrate your measurement method, but the data, the reference data of your model show me that your frequency is very correct. So I would like to ask that since your model, there's always some difference around 5 to probably 10, I'm not very sure, % of the difference between your model and your experiment measurement result, the frequency. So do you have any comment that this is just due to some measurement error, or is there some physical reason?
I think that maybe will be the white noise, or another example will be the I would say that's the H tone as the air cooler resistance. I mean the slit of the disc, and it will have the frequency, but in our analysis, the frequency of it will become as maybe like a higher frequency, called that maybe higher than 100 Hertz. So in our situation, my experiment result was only in 100 to 700 range. So I think the H tone wouldn't affect the result.
How about the other two teams? Do you have any comment about the errors?
I think that I agree with the reporter for the explanation. I think that maybe there's some measure error in the experiment, but I also agree with the theory.
I disagree because the white noise doesn't have specific keys, so that there must be some other reason that causes the specific key. Yes.
Sorry, another short question to only talk for the reporter. You show us the console simulation. So do you see anything worse to mention, or can you demonstrate the consistency with your result? Because I cannot see that. What do you want to say with the simulation?
I just want to say when you have a different situation, that maybe this will be shown at different rotational speed, and you can see that when you're.
So do you confirm it with your experiment?
No, I just want to show the
air. Answer yes or no.
Yes.
You confirm with your.
No. Sorry.
Yeah, please.
Reporter, can you go to page 41? 41. Here you show us a linear relationship.
Yes.
But maybe from page 32 to 41, you use a lot of linear relationship. So can you tell us the physical origin or the physics behind why you can use the linear relationship to fit your data?
Because you see, as the function shows, that the NP equal to QR is simplified with the function of SO function and cosine part. And when we put the n equal to 1, we can get the NP equal to QR, which under the fundamental mode situation. And then you can note
That would be the, okay, thank you. So please go to page 32. Sorry, maybe 31 or 33. Okay. Okay, so let me go back to that linear fit. So with your linear fit, it implies that
Please go back to 41.
As increasing of speed or the number, then the frequency will also increases. So is there any limitation or?
Yes, the simulation was, I will do, but I didn't show it in my presentation.
Okay, any question? Yeah, please.
I think Euro have a lot of data, and I think it's very from your result. I think the linear fit is okay. Yeah, it's good. But however, the problem says how the sound characteristics. Okay, sound characteristics depends on the relevant parameters. Yeah. So that means you kind of understand the sound created by your instruments, right? Yeah. I think you all agree. He presents several different parameters to characterize the sound. I just want to know what's the difference between the regular sound and the sound you make in here. What's the difference? I think three of you should answer the question.
Because your sound will be maybe like a simple sine wave or maybe like a complex wave, and they also can be the same frequency as you're hearing, but you maybe will feel that will be the different sound because the amplitude will affect the waveform of it. So I make sure that amplitude and frequency to show that there will be the different sound, but they still can have the same frequency. So what's the frequency and amplitude? Maybe for some phase or another, but yes.
Without any holes, there will be a fundamental amplitude, like I just mentioned. But with the holes, when there is a compression wave passing through, the atmosphere is just like a wall stopping the airflow to progress. So, as I mentioned, there will be a stationary wave, and the stationary wave will occur the overtone frequency. So I believe that there will be more overtone frequency with the same distance of frequency difference, and the amplitude will gradually decline.
Okay, so because of the compression wave, the shape of the wave will change. And because the shape of the wave will change, that the overtones and the overtones will also change. But the fundamental frequency will stay the same. So it is like the overtone difference.
Okay, I think I have a short question.
Short question to a reporter. From this experimental 2 and also experimental 4, actually you say it won't affect the frequency, but it makes the sound louder. Can you tell us how can you draw this conclusion that your sound becomes louder from the data you show here? From your theory and experiment.
You can see that in my SNP analysis, like the y-axis will be the amplitude. As you can see, that it will become louder. From different.
So do you have a graph? The vertical amplitude is the amplitude, and the horizontal is the.
No, I didn't analyze a single amplitude figure.
Okay. Okay, I think we can move on to the scoring part.
Okay, since the scores are already, so we start from the reporters' scores, please. So the scores are 6, 7, 8, 7, 8, 5, 7, 7, 7, 8, 7. And the scores for the opponent, please. 5, 7, 8, 8, 8, 5, 6, 7, 7, 8, and 8. And the scores for the reviewer, they are 6, 8, 8, 7, 8, 8, 7, 7, 7, 7, and 7. So I think we can give some comments. For the reporter, we have a single 5 and some 8. So how about the 5? Thomas, please.
So for the reporter, you actually did a very good experiment, but you consider what you consider is not enough, and the parameters and also the experiments, you cannot give us a very conclusive, and you also didn't give some boundary conditions, such that for me it's a little bit diverse.
Okay, so we got the 3, 8. So are there any comments about the 8? No comments is okay. So, but if there are. Okay, so about the opponent, we have 2, 5, several 1, 6, several 7, and 5, 8. So about 5, any comments?
So for the reporter, for the opponent, so the 5 comes from the discussion, because during the discussion, so basically I feel that you didn't listen to the reporter's explanation. You just try to make your statement. But that should not be this. And also from some of your point, basically, you will have the same understanding as the reporter. So that's why you got the 5 on me.
So any comments about the 8? No? Okay. About the reviewer, we have a single 6 and a lot of 7 and 8. So any comment about your 6?
The 6 basically comes on 2 points. First is that for your pros and cons about the report. So that if you mentioned that the point you mentioned is not that relevant, that is one point. Secondly is that during your report, I don't see your opinion. Basically, for example, you say that that is mentioned in the report. That is not your opinion. That is the reporter's opinion. So such kind of stuff. So that will make you into 6.
Okay, as a non-scoring juror, I think I can give some comment about the opponent's performance this round. That the opponent emphasized a lot about the standing wave. Okay, but I think that you didn't mention about why you think it's a standing wave. Yeah, because I think partly because you see the spectrum, you see a lot of spike. And since there is a spike, it means there is some special mode. And the spike appeared with the equally spacing in the frequency. Usually that means you have certain cavity. Okay, so I think you failed to point it out, that part. So I think that's a kind of a pity. But anyway, I think we already finished the This is fight this morning. So I would like to thank all 3 teams and all
hardworking jurors. So let's give a big hand to all of them. Okay. So the session this morning will be closed here, and some announcement and notice about the lunch and the closing ceremony this afternoon. I will switch back to Mandarin. 我们等一下我们中午会提供餐盒会在门口那边发放。那我们有借一些地方给大家用餐第一个是对面的综合大楼的2楼。那大家可以去那边吃东西，但是它没办法容纳所有的人，所以我们还有另外2个房间，一个是在物理系门口那个文会厅，然后另外一个是物理系里面的会议室在